Hi guys. So in this video, I'm going to show you a question. This question right here, I believe it's relatively straightforward, but it is quite interesting in the sense that there is a little bit of a trick to solving this question. It might mislead you first, like if you know what a slant asymptote is, and if you know what these definitions really mean, it actually might be the fact that you have prior knowledge might actually mislead you towards concluding that a particular statement is, for example, true when it's in fact false, or it's false when in fact it's true. Let's see what the question is. So the question says, let f be a function defined on R. So this is just typically defining what a function f is. And it says that we say f is a candy cane at infinity if there exist real numbers a and b, where a is a non-zero real number, such that limit as x approaches infinity of f of x divided by ax plus b is equal to 1. So this is just a new definition. The question is just giving us a new definition of what it means for a function to be, let's say, a candy cane at infinity. So in this case, it's saying that a given function is a candy cane at infinity if there exists a non-zero real number a and a real number b, such that limit as x approaches infinity of f of x divided by ax plus b is equal to 1. So in order, just to give you an example, let's say I have the function 2x plus 3. And I ask you the question, is this a candy cane at infinity? The answer would be it is, because while I can pick a to be 2, so if I pick a to be 2 and I pick b to be 3, then I'm going to get limit as x approaches infinity of, well, f of x divided by ax plus b, where this is f of x and this is ax plus b, is simply equal to 1. So this is clearly, I mean, the function 2x plus 3 is clearly a candy cane at infinity. Okay. So this is what the definition means. If you want to know what the definition means, like more intuitively and not with an example, then what it's simply saying is that as x approaches infinity, the functions f of x and ax plus b are growing at the same rate. So they are relatively growing at the same rate. Or you could even say that, I mean, this is really non-rigorous, but you can say that at infinity, ax plus b is practically the, or effectively the tangent line to the function f of x. Okay, so it says, is each one of the following statements true or false? If true, you have to prove it, of course. And if it's false, you have to show it with a counter example. Let's begin. Let's see what part A says. So part A says that if f has a slant asymptote at infinity, then f is a candy cane at infinity. So before I ask you to pause the video and try to attempt this question on your own, I'm gonna actually state what it means for a function to have a slant asymptote at infinity, because I believe that especially if you're someone who's in high school, you probably actually don't know the rigorous definition of what a slant asymptote is. So here's the definition. So f has a slant asymptote, a slant asymptote. You could say at infinity, if and only if this condition is satisfied, there exists a non-zero real number c. Well, just to state that this real number does not actually have to be non-zero. It can be a real number that is actually equal to 0. Over here, c can actually be equal to 0, but the question explicitly states that a horizontal asymptote is not considered a slant asymptote, only for this question. In reality, a horizontal asymptote is actually just a special case of a slant asymptote, which is why we allow c to be equal to 0. But in this case, if you allow c to be equal to 0, you're just going to run into some issues with the actual question. So we overlook the fact that a horizontal asymptote is also just a special case of a slant asymptote, and we're going to assume that a horizontal asymptote is not a slant asymptote, which is why we need to assume over here that c is not equal to 0. Okay, so there exists a non-zero real number c, and there exists a real number d, such that limit as x approaches infinity of f of x minus cx plus t is equal to 0. So if this condition is satisfied, then we can conclude that the function f has a slant asymptote at infinity. So let me see if I can give you an example over here. Okay, so pick up any function, or you can just go ahead and pick any function that has a slant asymptote at infinity. So for example, I'm going to pick the function. Okay, I'm just going to pick a function over here. I'm going to say let f of x be equal to x. If you don't know, then every linear function, is a slant asymptote of itself. So this is a trivial example, but I believe it's gonna convey the basic idea. So let's see that. So let's say that I want to figure out if this function has a slant asymptote at infinity, and I claim that it does have a slant asymptote at infinity. So I'm gonna use this definition over here to test if this function has a slant asymptote. So what I'm gonna do is instead of c, I'm gonna put 1, and instead of d, I'm gonna put 0. Let's sub everything back in. So I'm gonna get limit as x approaches infinity. Instead of f of x, I'm gonna put x. Instead of c, I'm gonna put 1, so that's just x. And instead of d, I'm gonna put 0. And you can see that x and x is gonna cancel out, and I'm just gonna get that limit as x approaches infinity of 0 is 0. It clearly satisfies this condition. In other words, there do exist a real number c and a real number d, such that limit as x approaches infinity of f of x minus cx plus d is equal to 0. And therefore, the function f of x equals x does have a slant asymptote at infinity. And what is the slant asymptote? That slant asymptote is just equal to y equals cx plus d, which implies that y is equal to x because d is 0 and c is 1. So this is how you generally use this definition in order to figure out whether or not a particular function has a slant asymptote. Of course, this was a very trivial example. There are harder examples out there that you can refer to. Okay, so let's come to part A now. So part A says that if f has a slant asymptote at infinity, then f is a candy cane at infinity. So let me just tell you what this question is really asking you. What this question is really saying is that given or assuming that f has a slant asymptote at infinity, in other words, we can assume that this condition is true. In other words, we can assume that there exists a non-zero real number c and a real number d such that limit as x approaches infinity of f of x minus cx plus d is equal to 0. So we can assume that. Now, what the question is saying is that given that you can make this assumption, is it also true that the function f must be a candy cane at infinity? In other words, should there also exist a non-zero real number a and a real number b such that limit as x approaches infinity of f of x divided by ax plus b is equal to 1? What part B says is that if f is a candy cane at infinity, then f has a slant asymptote at infinity. In other words, what part B is now saying is that if we can assume this condition, so if we can assume that f is a candy cane at infinity, in other words, there exists a non-zero real number a and a real number b such that limit as x approaches infinity of f of x divided by ax plus b is equal to 1, then can we also assume that f has a slant asymptote at infinity? In other words, that can we also assume that this condition is satisfied, or can we also conclude that this condition is satisfied? Okay, so in this video, I'm only going to present the solution to part A, and I'm going to leave part B to you. But before I do that, at this point, I'm going to ask you to pause the video and see if you can solve part A on your own. So by now, I hope you've attempted part A on your own. This is actually a question from one of my problem sets, by the way. It is a relatively simpler question. I will show you some of the more harder questions from my problem set as well. But I believe that these true or false questions do tend to, really force critical thinking as opposed to some of the other harder questions. Anyhow, so let's begin with the solution to part A. So first of all, we have to conclude whether or not this is true. And if you believe that if you concluded this is true, then you're absolutely right. This theorem is true. So it is true that if f has a slant asymptote at infinity, then f is also a candy cane at infinity. So this statement is true. I'll present a proof for it. So this is how, if you're doing such a question on a assignment or a test, this is how you would write out your answer. So the first thing is I'm going to say that this statement is true. This statement is true. And now I'm going to write a proof for it. So let's see what my proof is. So my proof is going to go as follows. First thing I'm going to do is define all my variables. So the only variable I have over here is the function f. So I'm going to say let f be a function defined on R. The next thing I'm going to do is state all my assumptions. The only assumption is that f has a slant asymptote, because, well, the question says that if f has a slant asymptote at infinity, in other words, assuming that f has a slant asymptote at infinity. So I'm going to assume that f has a slant asymptote at infinity. So in other words, what this simply means is that there exists a real number c and there exists a real number d such that limit as x approaches infinity of f of x minus cx plus t is equal to 0. So this is what it means for, of course, f to have a slant asymptote, and I'm going to label this to be 1. So let's say that this is condition number 1, and I want to show that f is a candy cane at infinity, or in other words, there exists a real number a and a real number b such that limit as x approaches infinity of f of x divided by ex plus b is equal to 1. Okay, and let's say that this is condition number 2. Okay, so the first thing, of course, that I have to do is figure out what my a and b will be, because I need to state, well, this is my real number a and this is my real number b. In order to do that, the first thing I'm going to say is let c and d, so to be more precise, let c be a non-zero real number and d be just any real number. Let c and d be real numbers that satisfy condition 1. Okay. And no, this is just me being rigorous over here. I just want to make sure that okay, in proper mathematical terms, the issue is that these although I've already stated over here what c and d are, these are quantified variables. So as long as they are not like dequantified, I cannot use them in the rest of my proof. So which is why everything that is stated in your assumption is quantified. So any arbitrary variable that you are stating in your assumption is a quantified variable. Before you can reuse it in your proof, you need to basically dequantify it, and this is just me dequantifying it. I'm now explicitly stating what c and d are. So I'm saying that c and d are now the variables that will satisfy equation number 1, and I know that they have to exist such real numbers c and d, because by assumption f is a slant asymptote, so I know that such real numbers have to exist. And then I'm going to say let a be equal to, or take a to be equal to b, take a to be equal to c and b to be equal to d. In other words, I now must show that limit as x approaches infinity of f of x divided by cx plus d. So instead of ax plus b, I'm now written cx plus d because I took a to be c and b to be d, is equal to 1. Okay. And this is where the proof actually begins. Note that I already know that limit as x approaches infinity of f of x minus cx plus d is equal to 1. I know that this is already equal to 0. This just follows from the fact that f of x has a slant asymptote. So limit as x approaches infinity of f of x minus cx plus d is 0. So I'm just reusing that over here. Okay. Now what I'm going to do, and this is where the manipulation comes in, I'm going to factor out a cx plus d. So I'm going to write it out like this: cx plus d times f of x minus, sorry, f of x divided by cx plus t minus 1 is equal to 0. So all I've done is I've factored out a cx plus t. Now notice that since c is non-zero, I can write it out over here. Since c is not equal to 0, limit as x approaches infinity of cx plus t is either equal to positive or negative infinity. However, since limit as x approaches infinity of cx plus t times f of x divided by cx plus t minus 1 is equal to 0, it must be the case that limit as x approaches infinity of f of x divided by cx plus t, minus 1 is equal to 0. Okay, why should this be true? Well, the idea is quite simple. You have a product of two functions over here, right here. You have a product of two functions. And you know that as x approaches infinity, one of these functions is going to either positive infinity or negative infinity. But what you also know is that the product of the two functions is going to 0 as x goes to infinity. So if this second function, that is f of x divided by cx plus t minus 1, goes to infinity or to negative infinity or to any non-zero number, you know that the product of the two functions will also go to either infinity or negative infinity. Therefore, for the product to go to 0, it must be the case that limit as x approaches infinity of f of x divided by cx plus t minus 1 goes to 0. So you can, if you want to be a little bit more rigorous, you can argue this by cases. So what I mean by that is you can first assume that f of x divided by cx plus t minus 1 goes to infinity, and show that if this is the case, then this limit cannot possibly go to 0. Then use negative infinity, then say that it goes to some positive real number, then it goes to some negative real number, and in all these cases you'll see that this limit can never equal 0. This just follows from the fact that you have an indeterminate form, or you need to have an indeterminate form in this step over here. This needs to be an indeterminate form. Okay. So now, since this once you have this established, that this must be equal to 0, after this the proof is very simple. Notice that this will imply that limit as x approaches infinity of f of x divided by cx plus t minus 1, and I'm just going to add 1 on both sides, right? So this must be true. And now by the limit law of sums, so you should write down by the limit law of sums, I can just bring this 1 inside. So I can say that f of x divided by cx plus t minus 1 plus 1 is equal to 1. And this just follows from by the limit law of sums. This is just simply true. And now this one is going to cancel out, and I'm going to get limit as x approaches infinity of f of x divided by cx plus t is equal to 1. And of course, this just completes the proof, because this is precisely what I wanted to show. Remember that once I had picked my a to be equal to c and my b to be equal to d, all I had to show to prove that this theorem was true, that limit as x approaches infinity of f of x divided by cx plus t is 1, and that I've shown over here. So what does this theorem really mean? Or I mean, like, what is the idea behind this? Or once I've proven this, what have I actually shown? What I've shown over here is that given a function, so given a function f, what I've shown is that the following is true. If limit as x approaches infinity of f of x minus, let's say, ax plus b is equal to 0, where I must say that a is a non-zero real number, So A is a non-zero real number and B is just any real number. Then if this is true, if limit as x approaches infinity of f of x minus ax plus b is equal to 0, then limit as x approaches infinity of f of x divided by ax plus b must also equal 1. Then this must also be true. So if you know at any time you tell me that you have a function f such that limit as x approaches infinity of f of x minus ax plus b is equal to 0, then I can immediately conclude that that function must also satisfy the condition that limit as x approaches infinity of f of x divided by ax plus b is equal to 1. Okay, yep, and that's pretty much it with part A. I'm going to leave part B to you. I'm going to just give you a spoiler. Part B is false. The theorem does not work the other way around. If f is a candy cane at infinity, which is what we're assuming over here, that f is a candy cane at infinity, then f does not, then, I mean, there exists a function f such that f is a candy cane at infinity, but f does not have a slant asymptote at infinity. I'm not going to give you the counterexample in this video. Instead, I'm going to ask you to see if you can come up with a counterexample on your own and prove that the counterexample actually works. And when I say that prove the counterexample actually works, what I'm essentially saying is that once you've written a counterexample or once you have come up with a function f that you believe is a valid counterexample, show that f is a candy cane at infinity. In other words, show that that function f satisfies this condition, and then show that f does not have a slant asymptote at infinity. In other words, show that this function, that the function that you have come up with does not satisfy this condition. And yeah, if you have a valid counterexample, leave that down in the comments below. And if the counterexample you come up with is a valid counterexample, I'll let you know in the comments below. And yep, that's pretty much it for this video. I'll see you in the next video.